Good evening, ma'am.
Good evening. Okay, it looks like we're live now. Okay, I think this is the most people that we've had in a live session at once. Welcome to Arvind and Gargi as well. How you all doing? Okay, I'm just going to assume that everybody is doing fine. And I don't know if can you let so I think Naveen already said that he has some specific doubts, and I think we'll definitely be going over those just so that I can plan my time. Uh, the rest of you, do you also have specific questions that you want to ask? Then maybe just um, in the interest of keeping it organized, I can plan to rotate. But if you're just here to tune in and maybe pick up some last minute tips, then I will just maybe summarize a little bit of how the exam is structured and so on. So let me know, Vikas, Arvind, Gargi, did you have any questions or doubts, or were you mostly here to just listen?
I think I was here mostly for tips and like
Okay,
advice, but no
awesome.
specific doubts from my side.
Take care. Okay, that's great. That's perfect. Arvind, what about you? Sorry, I don't mean to put people on the spot. This is just to help me plan. You can also, if you can't unmute yourself, you can also put your response in the chat. That's also fine. Vikas, what about you?
Ma'am, even I was here for the tips and general
Are you
advice,
okay?
but I was having some issue with the direction in which reductions go.
Okay. Yeah,
So,
that's a common point of confusion. So I'll try to once again emphasize what is happening with that a little bit for sure. And okay, so Arvind, you said that you're not in a position to chat, and that's fine. If you did have any specific questions, you're welcome to put them in the chat. Otherwise, I suppose you can just hear us out as we go along. You know? And yeah, I will see if I can set up a screen share where I can connect my iPad. But in the meantime, um, okay, I'll just take maybe 2 3 minutes to talk about some general aspects. I think because I okay, so I will first of all admit that the second half of the course is a little bit experimental because we didn't have a sense of what kind of backgrounds people are coming from. So the way this was designed was the first half builds on and revises and strengthens what you already know probably from your PDSA course, but it's just that we went a little bit deeper, so more examples and things like that. So I think up to week 6 or so, probably you would have found it kind of comfortable. But week 6 is where we started with NP completeness, and I think that's where things start going a little bit, being a little bit different and probably a little more abstract. And we have found even in the last run that reductions is one sort of turning point where things start to get a bit. Maybe a little bit even confusing, or that's perfectly natural. It takes a little time to get used to it. And then after that, I think some of the course content has been experimental and you haven't been exposed to all of it as well. But I think basically you've seen a little bit of ideas from randomization, approximation, and exact algorithms. I think that's been the situation. And I think we released some content on parameterized algorithms, but we won't be testing you on it because we didn't have enough time to really absorb it through assignments and things like that. So the focus of the exams is really going to be on, mostly it's going to be heavy on the first part, including reductions. And then I think there'll be some very basic questions from, approximation, randomization, and exact algorithms, branching, and things like that. I think there'll be not too many questions from those, and whatever will be there will be like, I think the videos are also there. There is not much going on there. And I think the only maybe one thing that may have been a little bit challenging may have been the inclusion and exclusion kind of principle things around that. So possibly, that's one thing that may have required a little bit of getting used to. But yeah, in terms of the exam, we have tried to keep it simple on the material that was hard, and I think there isn't a lot of weightage also on the second part. So that's the only off the top of my head, so it's been a while since we prepared the exam, so I can't give you any concrete breakups right now. But I think at a high level, I can tell you that this is the bifurcation. So if you have limited time and you want a strategy, I would suggest preparing more from the first half, like what you have done for quiz 1 and 2. That should already put you in a good position for the exam. So as far as a very high level tip goes, that's what I would like to say. And I think there was some mention about reductions, and I'd probably say this better if I have if I have some kind of a screen share. But let me just verbally articulate the one thing that you need to remember, which is that when you reduce from a problem A to a problem B, what is basically happening is that you can use solutions for B. If you have an algorithm for B, you can use it to solve A. That is what is happening. So just remember this conceptually, right? When you go from A to B, what is happening is that how can you solve for the problem A? Somebody gives you an instance of A. What you can do is you will feed it to this reduction machine. The machine will output some instance of B. And now, if you have an algorithm for B, then you can take that algorithm and use it to solve whatever this machine gave you. And you have a solution for B. But because of the way reductions are defined, they preserve equivalence. So this answer for B can also be reported as the answer for A that you started with, the instance of A that you started with. So this is the basic philosophy of a reduction, that you can use solutions for the target problem to solve the source problem. Now, there are two ways that you apply reductions. One is to say that, okay, here is a target problem that I know how to solve, and here is a problem I'm struggling with. So I will reduce to the target problem to take advantage of the solution that I have. Okay, so we did this when we did flows, right? Very often we would take a problem and we would reduce it to the max flow problem because we knew how to solve max flow and we wanted to take advantage of that. But you could also say that, okay, here's a problem I'm struggling with. I suspect that it's a very difficult problem and maybe there is no polynomial time algorithm for it. Then what I will do is I'll take a problem which is well known to not have a polynomial time algorithm so far, and people believe that it does not have a polynomial time algorithm. So something like SAT, independent set, vertex cover, you can pick your favorite NP complete problem. You take such a thing and then you reduce it to your problem. So now what you're saying is, if somebody comes up with an algorithm for my problem, then that can be used to solve an instance of this problem that is famously hard. And therefore, it is very unlikely that somebody can solve my problem easily. So it's the same construct, it's the same philosophy, but it's being used in two different ways, depending on what you have and depending on what you want to show. So I don't remember who had the question about reductions. Maybe it was Vikas. Does this help, or did you have any sort of more specific questions around the framework? Okay, that's awesome. So in terms of the direction of the reduction, I mean, just remember that you always reduce, either from a known hard problem to your problem, or you reduce to an easy problem. So if you want something that you can learn by heart, then this would be the thing to learn. But hopefully you can also verify it quickly conceptually in terms of what is actually happening. But if you just want a mnemonic, yeah, reduce from a hard problem or reduce to a easy problem. Those are the two things that make sense to do. Okay. So, all right. So, I think I'm done with whatever higher order tips I wanted to give, and I'm also done with responding to this thing about reductions. What is the direction of a reduction that's useful? And now maybe we can just move on to addressing. I think Naveen. You had some questions that you had come prepared with, right?
Yes, ma'am. So can I share my screen?
Oh yeah, absolutely. Please do that.
So my first confusion is with this question, which is from graded assignment 2 and question number 2.
Right.
Actually, I could not understand the option B properly. Like I just couldn't.
Yeah, figure out what it meant. Okay, yeah. So actually, to be honest, I think if I'm not wrong, this is one of the practice or review assignments. Is
It's
that right?
a no, no. It's a graded assignment for week 9.
Oh, I see. Okay, it's a graded assignment. Okay, so I think here the intention was to give. I mean, the broader intention was to get some more practice with with some kind of dynamic programming plus I think we were also trying to apply the inclusion exclusion principle, but in a slightly more advanced setting. So anyway, let's go over what's going on here. So right. So what we are saying here is that the input instance can be simplified in the following fashion. If you have a terminal vertex which is not okay, let's see. So if you have children, if you have terminal vertices which have children, then you can come up with an equivalent instance where you can get rid of it. Okay, for me, I think I really do need to be able to share my screen to explain this one properly. So just give me 1 second to see if I can connect it. The other thing is, okay, so this one actually, maybe I can just give you a little additional context and go over the whole thing properly, because this question, as far as I remember it, is actually is a slightly non-trivial question. So I'd like to maybe do this. If you don't mind, let's come back to this at the end and go over it, walk through it properly. Do you have some other questions that you would like to go through in the
Yeah,
meantime? Can we do that? Yeah?
yeah, for sure.
Okay, thanks.
So this is yeah, like from review assignment 1, question 2. Okay, so in this question, is it readable, ma'am, or should I zoom in?
It's kind of readable. That's fine, I
Okay,
think.
so
So,
I
yeah.
was confused about this exchange property. How does this apply to this situation?
So I'm not sure if this was okay. So I vaguely remember that there was one question which needed to be fixed, which we had discussed in the forums, and I don't remember if it's this one. Let me go through it and see if I can, if the answer is even correct or not. Let's see. So what we are saying is, so the longest path in the subgraph induced by S has at least 3 vertices, and we're not saying, for example, that S has to be connected or anything like this. So what the exchange property says is that if you have, so I think here this is, okay, let's just go over all the properties, I suppose. So you would, if you have a set S which has a path that has at least 3 vertices, all subsets of the set need not have this property, because you could just pick out subsets that don't have long paths. So heredity is not satisfied by this family. Do we agree on that?
I think heredity, yeah, is not satisfied. Yeah.
Heredity is not satisfied. However, with the exchange property, I think we will actually not have a problem, because if you have 2 sets A and B, and size of A is strictly bigger than the size of B, then what we want to say is that you can take some vertex from A and pull it into B, and B union that vertex is still an element of the family. Now, the point is that if B already has a path of length at least 3, by pulling in one more vertex, you're not going to destroy that path, right? So I think it does satisfy the exchange property, and maybe Arup, we can make a note of this. This was in the last run. We had discussed that this answer key needs to be updated. So I think the exchange property is indeed satisfied in this one, and we are asking what is not satisfied. So I think the original answer key was like this because I had a slightly different version of the question in my mind. I think I was also saying that a subset of vertices belongs to F if it's connected and has this property. And therefore, the issue is that you may not always be able to bring a vertex in while still maintaining connectivity. So I had some counter examples of that sort, but the word connected is not mentioned in the question. So for this version of the question, the answer that you have given is actually the right one. I don't know if I don't know how reevaluations work or whatever, but I think we should at least update the answer key, right? So so Arup, can we just make a note of this, please?
Yeah, which should be the correct answer here?
It's just what what Naveen has answered. It's just heredity that is violated, nothing else.
Okay, the B.
Yeah.
And so the next doubt is from R.A. Should we move to that, ma'am?
Sure, yeah.
Yes, so this question is something like which we had 2 versions of this question.
Right.
And I still cannot understand how to do this actually. I referred some online material as well, some discussions online, and I
Okay.
found that in all those discussions, whatever example they were, like they were all like kind of false, because they said there should be no relation existing between the two. Uh,
Okay. All right. So let's, okay. So maybe let's just read it and go over it because I also need to jog my memory of what the setting of the question was. Okay. So let's see. So we have said that, Raj has proved that algorithm one, his algorithm is a two approximation algorithm, and Lata has proved that her algorithm is a four approximation algorithm, right? And now we are saying there must be some input for which the performance of algorithm one is strictly, I mean, the output of algorithm one is strictly less than the output of algorithm two, right? So this is the claim. And now let's think about this. All we are saying is that, um, okay, so all we are saying is that Raj has managed to come up with a proof that the output of algorithm one is always within twice of opt. Okay, so it's a minimization problem. So you're trying to prove you're trying to find the smallest thing that satisfies the smallest solution, right? That's what we're trying to do. So there is some opt, which is the true opt, and out one, which I will use to denote the output of alg one. All we know is that out one is at most two times opt, and we know that out two, which is the output of algorithm two, is at most four times opt. These are the two things that we know. However, these inequalities may not be tight in the sense that this analysis may not have been tight, right? So we know that out 2 is at most four times opt, but it's possible that Lata's analysis is not the best possible. Maybe it's a lazy analysis, and it's possible, for example, that, uh, it's possible that out 2 is in fact, let's say, 1.5 times opt. It's just that this proof does not show it, right? But
Mhm.
the true solution may be much closer to the opt, and it's possible that Rad's algorithm is really doing something stupid and it's always outputting something that is twice of opt, right?
Mm.
If that is the situation, then there may not be any input for which alg1, the quality of alg1 is actually strictly better than the quality of alg2. Does that make sense?
Yeah.
All we are saying is that you have an inequality which says that out2 is at most four times opt. But we don't know that there is an input on which out2 is actually equal to four times opt. Right? It's possible that you saw the algorithm and you came up with some reasoning saying that okay, this is always within four times the optimal. But maybe the performance of the algorithm is actually much better. It's always very close to opt. It's just that you have not come up with an argument to show that, right? So just because you have these inequalities, it doesn't mean that the inequalities are tight. If additionally we knew that, Lata has proved this and she has proved that the analysis is tight, meaning she has come up with some instance where
Mm.
the algorithm indeed performs badly, indeed is, away from the opt by a factor of four. And then you could say something like this, right? Then you could say on that input, Raj's algorithm will definitely output something smaller, right?
Yeah.
But it is not given here, right? So the analysis could be loose. That is all that we are saying. It's really a simple, stupid thing. That's all.
Yeah. Yeah. So because of that, like I answered this as well as false.
Okay,
Yeah.
so let's see what's going on here. So we have that alg one is the out. Okay, so what we have here is out one is at most five times opt, and out two is at most 10 times opt, right?
Yeah.
So this is just a chaining of inequalities to say that what can we say about alg 1? It is at most um, okay. What can we say about alg 2? It's at most 10 times opt, right? um, this is actually in fact a very loose kind of inequalities. The question is this true, right? Alg 1 is at most five times alg 2. What do we know about alg 2? We know that alg 2 is at most what? It's at most 10 times opt, right?
Yes.
So when we chain these two inequalities, what we are saying is alg 1 is at most alg 2, which is in turn at most 10 times opt. So this is actually at most 50 times opt. So, but we already know that alg1 is at most 5 times opt. So this is easily true, right?
Okay.
Does that make sense?
Yeah, actually, I'm confused about like where this 5 is coming from.
So I think this was actually one nicer way of putting this question would have been to say that alg2 is at most 5 times alg1. I suppose that would have been, or in fact, 2 times alg1 if you wanted things to be tight. But as it stands here, 5 is not coming from anywhere. It's just some random constant intended to. So basically, I think here the important thing is not so much the constant. It's the important distinction is between like when can we say for all and when can we say there exists, right? So here we are trying to say that for all inputs, algorithm one has a certain has a certain guarantee on its performance, right?
Oh,
And in fact, it's the better approximation algorithm. So we are saying that alg1 never performs worse than 5 times another approximation algorithm, which is even worse than alg1. So in this case, this inequality is actually kind of easily true. Intuitively think of it as alg2 will give something, in general worse than alg1. But okay, I mean, again, it may not be a tight, sort of argument. But what we know is that alg2 is never worse than 10 times opt, right?
yes.
That is an upper bound, correct? So all we are saying is alg1 will never perform in some sense worse than. Okay, so maybe I should be a little bit more careful here. So we know that, okay, so if we just write down the inequalities, what do we get? We know that alg2 is at most 10 times opt, right? And let me just give me 1 second here to make sure that I'm getting the directions of the inequalities right. Sorry, I think I just lost my tab here. Okay, so right. So what we know is that for all, so let's just maybe start off by saying that for all inputs I, we know that alg1 of I is at most 5 times opt, right?
Yeah.
That is just basically by definition. And now the question is, can we say that opt is at most the output of alg2 because alg2 can never output something better than opt, right?
Yeah.
Because it's a valid algorithm, right? So it couldn't output something whose value is smaller than opt. That will violate the definition of opt. Right?
So that would mean that if we remove this 5 as well, then that statement would still be correct.
Okay, so I think let's be a little careful about that because then I think we run into the issue from the previous question. So I think for now, let's just do it with the 5 to make sure that we are on the same page. From just the definition that's given right after the question, right? We are saying that if it's a 5 approximation, then it means that the output is always within 5 of opt for all inputs. So just by definition, we have alg1 of I is at most 5 times opt for all inputs. Is this fine so far? That's just by the definition. So here in the statement that's been given, let's just replace alg2 of I with opt. And then the statement that you see will simply be the definition of a 5 approximation algorithm. Is that fair?
Yeah, ma'am.
Okay, great. So we have for all inputs I, we have alg1 of I is at most 5 times opt. So we have that. Now we can write opt is at most alg2 of I for any input. For any input I, opt is at most alg2 of I because opt is the smallest possible thing that you can have. So the output of ALK2 of I, even without using the fact that it's a 10 approximation algorithm, just using the fact that it's an algorithm that produces a valid output for this minimization problem, we know that ALK2 cannot beat opt. So you can write 5 times opt is at most 5 times ALK2 of 1. Does that ALK2 of I? Does that make sense?
Yeah.
So by chaining those inequalities, we know that this inequality is correct for all inputs. Now you're saying, can we drop 5? Well, okay, so ALK1 of I is, you're trying to claim that ALK1 of I is at most ALK2 of I for all inputs. Now this, well, I mean, the problem is with this that there could be some input on which ALK2 actually performs better than ALK1, even though it's the reason this is a 5 approximation and a 10 approximation is because that's the best that we could prove about these algorithms. And it's even possible that these analyses may even be tight in the sense that there may be some input on which ALK1 actually outputs something that is off by a factor of 5, and there may be some potentially another input on which ALK2 actually produces something that's off by a factor of 10. All of those things may happen, but the point is you're looking at the space of all possible inputs, and now these are now approximation algorithms, right? They're flexible. They don't have to always produce opt. So far, we've generally been seeing algorithms that always have to produce the right answer, but now that's not the case anymore. So it's very fluid. So on different inputs, ALK1 and ALK2 can do different things as long as they commit to this promise of always being within 5 and within 10 respectively. So there's this ceiling, there is this kind of Lakshman Rekha that they cannot cross, but within that they can do anything they want. So now it's possible that there is some input on which ALK2 actually comes closer to opt than ALK1. It may be intuitively unlikely, but technically it's possible. Does that make sense? That's why you cannot drop that 5.
Oh, yeah.
Okay. All right.
So should we move to the next question, ma'am?
Sure.
This was again from the same assignment. In this question 4, I got it correct because I used the error and omission technique, and I found that only like A was like very close to the correct answer, but then I could not make sense out of these symbols. Like, let me zoom it in.
Okay, that might work.
Here it says E is equal to. So I assumed that maybe this is some kind of misprint, that E is equal to E. Maybe this.
Yeah, that doesn't make sense even to me. I think that should have been E belongs to E. So E, the capital E is the set of all edges in the graph, and what we are doing is we have a variable corresponding to every edge. And if you just go back to the question, let me remember, what are we trying to capture? Okay, we're trying to capture a linear program that tries to find a maximum cardinality matching. Okay, so forget about the options. Let's just say, what are we trying to do? Right? So okay, so I'm sorry, I think if the options have misprints, that's not ideal, because I think the rest, okay, that's a very strange typo, because the rest of the options seem to have it right.
Yeah,
So
everything else was fine. Only the correct option was like, this was a very weird situation.
yeah, that is okay. So maybe, I don't know, I will request Arup to also look into this once. Maybe it's usually they take whatever whatever I give them typically, and these are usually screenshots from my papers. This is certainly my fault at some level. I'll go and double check what's going on. But anyway, so E belongs to E. You probably fortunately found mistakes in all the other ones, so you probably placed your bets on this. So yeah, this is not probably not a good situation, but we will get this fixed. But did you follow the spirit of what the linear program is trying to capture? All we are saying is, we have a variable which is set to 0 or 1, depending on whether, so at least the ILP version of it would be the following, that you're trying to figure out like which edges go into a maximum matching. Those will be 1 and the rest will be 0. But then you cannot put two edges in, you cannot put two edges in a matching if they share an endpoint, right?
Yeah.
So basically, the idea is to say that you take all edges which are incident on. So basically, for every vertex, look at all the edges that are incident to it, right? And you say that, well, among these, at most one of these edges can belong to the matching. That's all that we're saying. That's what the first constraint is saying. And then you have your standard non-negativity and integral constraints that comes from the relaxation of the ILP to ILP, right? So what is wrong with, maybe we can quickly go over what's wrong with all the other ones. So for the second one, the constraint says at least one. It should be at most one. You're not allowed to pick more than one from each. And I think for the third and the fourth one, if you scroll up a bit, I can try to take a
It
look.
is just minimization problems. Like the
As opposed to maximization. So it's the same thing except we're minimizing. So then if you minimize, of course, it's a bit silly because you'll set everything to 0 and it's a completely meaningless program. So those two are out. And here it's at least 1, which is not, again, it doesn't capture what we want. The constraint is at most 1. So sorry for the typos there, but basically it should be the same. It should be of the same form, that V belongs to E in the first constraint, and E belongs to E belongs to capital E in the objective function. So it's a good point. We'll fix those typos, but hopefully the meaning of the LP was clear, right?
yeah.
Yeah, I mean, I'm sure it was clear to you is why you picked out the right answer in spite of all the errors. So yeah, cool. Thanks.
Thank you. My next one. Okay, RA3 into RA4. I think. Okay, this was a long question. I still have to reattempt this because so I don't know if I should ask this or not. I did take some chances here and it turned out correct, but
Okay, good for you. So anyway, yes, I don't know if I want to spoil this one. I think if I remember correctly, this one is not, I mean, unlike the first question that I said we will defer, this one's actually, I think, a cute and doable question. So you might just want to take a look at it yourself. And yeah, as far as I know, it's a nice reduction. Should work out. Yeah.
also, can I ask you some questions from my previous end term paper, ma'am?
Okay, let's go over it. Yeah, sure.
There was some of them. I think this is the previous 245. Okay, this was covered.
Yeah, I think some of them were kind of overlapping from the assignments. Yeah. Do you want to go over this one?
Yeah, this one.
Okay, all right. So I think this one was again in the spirit of capturing what's happening with.
Oh, I think I did. I was able to do this one.
Yeah, but was it like, yeah, I mean, you're comfortably able to do it, or was something
No,
not clear?
it took me like the problem was that I was getting confused with because it was re-explained the same thing again. So I was reading the same statement again and again, and I was getting confused. So
Okay, all right. So yeah, I sometimes do this thing where I kind of repeat this in other words kind of thing, is just so that to double check the understanding of the first definition. कि अगर कोई confusion है तो it'll get cleared. So I'm sorry if it has this opposite effect of making it more confusing, but hopefully
yeah, this happened because the F was not mentioned in the first sentence, but it suddenly appeared in the second one.
Right. So here I think the style is basically saying that let F be a subset of edges, right? So instead of talking about any specific AI, I'm saying if generically F is some subset of edges, right? Then basically, yeah, maybe I think it's possible. So I don't want to use E because I'm talking about a subset of edges, right? So anyway, I don't know if you want to parse this, we can do it. But if you're confident that it made sense at the end, then we can move on.
Yeah, this is fine, ma'am. The next one was it was from this is the explanation of the question, and then I had a trouble with it's one of the parts of this question.
Okay.
So this is
Okay, we may have to come back to the question anyway, but you can go ahead and talk about the part that you had a problem with.
and this was 252. I couldn't make like that. Is this collection one factor over the set A is Metroid or not?
Okay. Um, right. Okay, let's go back. Collection of one factors. What do we mean by one factor? It means that we have yeah, okay. So in degree and out degree of every vertex is at most one, right?
Yeah.
So that means again, so if maybe it's related to the other question in a weird way, but okay, basically this is paths and cycles. Do we agree? This
Yes.
is the one factor. Yeah, so every edge is one incoming and every vertex is one incoming and one outgoing edge at the most. So if you just trace things, you will see that. I mean, you can prove it formally also, but you cannot have anything other than paths and cycles. And now the question was that do we necessarily form a matroid? And here, let's maybe think about, for instance, okay, so basically heredity will generally speaking not be a problem, right? Because if you have degree at most, out degree at most one and in degree at most one, if you look at a subset or a subgraph or whatever, you look at a subset of the edges, they will continue to satisfy this property. So heredity is a non-issue, non-emptiness is also a non-issue. So the only possible problem you'll run into is in the exchange property, right?
Yes.
Okay, so now we need to like think about how will we prove the exchange property. Suppose we are trying to prove it, right? So suppose you have two sets, both of which are one factors. Now the question is, can we always pull in something so that we can maintain that it's a one factor? I don't know if there's a counterexample here itself, for example. So let's look at the cycle on the left, right? So there's a 4 cycle. Now, let's say that you have yeah, I need to give you a bigger thing. So let's see if. So I was going to say that you can take the diagonal edge will not be possible to add to this one factor. But I need to expand that to a collection of 5 edges where I want to say that you cannot add anything to the base to the smaller set from the larger one. That's what I want to be able to say. Let's see. Okay, so maybe let's just take let's just take the top 2 edges, meaning okay. So can we imagine labeling this 4 cycle as 1, 2, 3, 4, starting from the top left corner and going clockwise?
If you want, I can annotate on my own tablet. I have connected it.
Okay, that's great. So you can do that, but it's actually okay. So I don't know. So I suppose you cannot see my cursor, but basically, I want you to think of one set which is just a path of length 2, right? And then another set which is basically just this diagonal. So basically, this triangle, right? But 2 edges in one set and the diagonal in the other set, right? So the set which has the 2 edges is the bigger set,
Yeah.
and the diagonal edge is the smaller set. So I have 2 sets, one of which has 1 edge and the other one has 2 edges, right?
Yes. Yes.
And the problem is that you cannot pull either of these 2 edges to expand on that diagonal edge, right? Because you'll either get a out degree violation or an in degree violation.
Yes. Yes.
So does that make sense? As a counterexample of the violation of the exchange property?
Yes. Yes.
Okay, good. So that would be why it's not a matroid. I don't know how well this will work in an exam setting, but I think when you try to prove that it works and you kind of get stuck, that would probably be a good time to start quickly thinking about counterexamples. And of course, you're putting in all this practice, so I'm sure that helps too. You see more examples like this, then when you see a new exercise, this kind of experience is useful. This kind of preparation that you're doing will be useful, I'm sure.
Thank you, ma'am, about this one. And then next one was 250. Sorry, 250. This is fine.
It was a dynamic programming question. Yeah.
Yeah, actually, I was able to do that. Earlier, I had just kept it for a revision purpose.
Okay.
I think that was all from my end, ma'am. Oh, sorry, ma'am. There's one more.
Sure.
About the inclusion exclusion principle formula that you gave us for the like intersection version of the formula.
Mm-hmm.
Actually, I tried to uh, make some like I tried to use it for and prove it for myself using two sets. For
Mm-hmm.
some reason, I was not able to make like prove it using Venn diagrams and all. So maybe I think my interpretation of the formula is wrong.
Yeah, I think with one version of the formula, what I remember is that the notation on one of them is a bit strange. So I should probably clarify that. Let's see. Like I said, I'm just going to try and join from the iPad. I've been trying to do that. Okay, I think Arup, I've sent a join request from the iPad.
Yeah, I have accepted.
Oh, I accepted it. Thank you. Okay, just give me a second. I'm just trying to figure out if I can share my screen. Okay, is this visible?
Yes, ma'am.
All right, let's see if, okay, I can actually write on this, except it's the wrong pen. Okay, all right. Now you'll have to give me 1 second to pull up the formulas that were there in the presentation. Okay, so the union version of inclusion exclusion, I think what we said was the following. So AIs are assets. And we said that the union is so looking at non-empty subsets. And then we have this addition subtraction thing going on here that's based on the parity set. And now we take the intersection of everything that belongs here. And the intersection version, same thing. So let me know if these are the formulas that you're talking about in terms of what you wanted to verify.
Yeah.
So this is AI complement. I'm writing it as U minus AI. Okay, so this is the so-called union version, and this is the intersection version. Now, just to be sure, is the union version okay? I think that I don't remember if we had a
Yeah.
special proof.
Union version was fine.
Okay,
The intersection version, which was like I was interpreting U slash AI as a AI complement.
correct. It is AI complement. I think the funny part of the notation here might be that what does it mean um, when we do intersection of, so here notice that we don't have this condition that x is non-empty, so x is non-empty will actually be a part of the sum, and we are going to think of sorry, x is empty is going to be a part of the sum, and there when you're saying we will take the empty set, right? So what does it mean, what does it mean that x is the empty set? um, Let's see. So this loop is empty, right? We are doing intersection over nothing, right?
Yeah.
So an intersection over nothing is to be interpreted as the entire universe. So that's a notational thing, and I don't remember if I'd emphasized this. But okay, like you said, maybe let's just try and do this for 2 or 3 sets and see if it makes sense, right?
Yes.
Right. Thing. And then the rest of it, I'm going to be lazy and say that if you believe the union version, you can get this using De Morgan's. I must have made some comment like that. But anyways, let's just as a sanity check, let's just write this down for n is equal to 2, as you said. So on the left hand side, we have a1 intersection a2. And on the right hand side, we have a sum of 3. So I guess we are looking at the set 1, 2. That's n. And how many subsets are we going to have? Well, we have the whole set, we have the empty set, and then we have the singleton. So we have 4 terms in our sum, and let's just go over them one by one. So when we have the full set, then that's going to be -1 raised to 2. So that will be a +1, and that's going to be the size of the intersection of I in 1, 2, AI complement, plus when we go with the singletons, it's going to be a minus. So it's going to be minus A1 complement minus A2 complement. And when we go over the empty set, it's going to go back to a plus because the empty set is 0. -1 raised to 0 will be 1, +1. And this whole expression here, when we are doing empty set, is the entire universe. That's the interpretation. So that's going to just be, you're going to think of that as U, size of U. Okay, so let's maybe do this in pictures, maybe a little bit easier. So we are trying to capture A1 intersection A2. And now we are writing it in terms of the complements. So first of all, okay, so maybe it's easier to, let me rewrite this once more. So size of U, we have accounted for everything. We are trying to count this fellow. Now we are subtracting A1 complement and we are subtracting A2 complement. So from the universe, when you subtract A1 complement, you subtracted all of this, right? So let's maybe look at it so far. Oops, I think I got rid of too much. Okay, so jab A1 complement we subtracted from the universe, what are we left with? We are left with just A1, right?
Yes.
That's what we have counted so far. Now we have subtracted A2 complement also, which means that, well, what have we over subtracted? Everything that is outside of both A1 and A2, that got subtracted twice, right?
Yes.
Because it got subtracted in A1 complement as well as A2 complement. But on the other hand, these fellows here got subtracted once, those that are in the symmetric difference, right? And what can we say about the intersection? I think the intersection would have survived, right? It did not
Yes.
get subtracted at all,
Yeah.
right? So now we need to compensate for over subtracting. Like, so right now this thing is strictly less than A1 intersection A2 because jo bahar tha, I mean, I don't know if it's okay to use Hindi, but everything here we have subtracted it twice. So this might even be a negative number. So we have to basically add that back, right?
Yeah. Actually, my mistake was not to take U.
Yeah, that's fine. So I think if you do a plus U, that fixes probably your computations.
Yes.
And yeah, regardless, let me just say that one more time, that when you add this, what are we adding? A1 complement intersection A2 complement. That's exactly the thing that we needed to correct for, which is everything sitting outside. And these fellows here would have basically not gotten subtracted at all. So the stuff in the intersection does not get touched by the subtractions, so they survive till the very end. The bad stuff gets subtracted, but some bad things get subtracted twice, so we add them back just as a correction mechanism. And like I said, I think if you want to prove this in general, there's probably like two ways that you can try to do that. One is we know the proof of the union, and then you just try to mechanically apply De Morgan's laws by taking complement. So that I think taking complement is a standard way of converting unions to intersections. So I think that is like a mechanical way of doing it. One thing that I haven't tried is probably you can also try and argue element wise, like say that take one element here which appears in the intersection of all the AIs, and again try to argue that that element gets counted exactly once here on the right hand side, just like we did for the unions, and then take something that is outside the intersection and try and argue that it basically gets cancelled on the right hand side. Yeah.
Yeah.
So I think those would be two ways of doing it. And I think it's worth trying. I think, to be honest, I don't know if I've tried it recently. I've tried it when I was maybe looking at it for the first time, and that was a while ago, but I assure you that it can be done. But yeah, the notation is a bit funny. I think, like you said here, you have to remember that x equals empty set is a part of the sum, and x equals empty set, this guy is to be interpreted as the size of the universe. Once you have that, I think your proof should go through.
Yeah. Yeah.
Okay, all right, super.
And then, yeah, that one question was left from week 9, ma'am.
Right, the very first question. So, okay, how about, I don't know if this is a good suggestion, and if it makes sense to you. Like I said, that is a question that does involve a few moving parts, and I think, okay, so I know you said that you had a question or a specific part which was about saying that the terminals can always be assumed to be leaves. That is sort of like doing some kind of pre-processing on top of the Steiner tree. But I will concede that that question is like a slightly longer story, and I think it deserves to be done nicely. And how about I record a separate short half-an-hour video just walking through that entire question and try to upload it in a day or two? Would that work for you guys?
Yeah, that will be perfectly okay.
Yeah, so then you can take a look at it offline. To be honest, I don't remember doing anything very Steiner tree specific in the exam, so you don't have to worry about it in a time sensitive way, but I'm sure you're just curious about it in general, and especially because it was a part of a graded assignment. I certainly owe you an explanation because it was a slightly harder question than usual, and maybe probably not. I mean, I don't know if all the phrasing in that question was helpful or not. So I will, I think, try to walk through it with you. And if yeah, like I said, I don't know how reevaluations would work at this stage because I don't think I heard any specific complaints earlier. I'm not sure if we processed anything, but if there is, we'll take a look at the data. And if it turns out that many people were thrown off by these questions, then we'll also try to see if we can influence the reevaluation a little bit so that everybody gets marks for anything that may have been confusing. Would that be fair?
Yeah, that will be perfectly fine.
Okay, all right. So I'll do a little bit of homework on that. And like I said, I don't think you have to worry about it from an exam point of view, but from a, let's understand what was in the assignments point of view. Please take a look once the video is up. I'll put it up. And if it's still not clear, of course, I'm happy to come back and have a chat, either over a session like this one or just even one-on-one. Yeah.
Yeah. Thank you very much, ma'am.
All right, that works. Sorry, I realized that we are close to being on top of the hour, and I think if I start talking about that, it's going to probably push this session well beyond. So I think it may be a good idea to take it offline. But I think, Arup, please remind me if I don't send you this video in a couple of days, okay?
Yeah, sure.
Okay.
Question number is which is
Question
think
number graded assignment 9, question number 2.
okay.
I think I remember this question quite well because it came up last time also. I think if you really are curious, maybe if you look at the live sessions from last time, I remember one of them, I think somebody similarly had a question about that particular problem, and we kind of went over it. But again, it was very spontaneous, and I think I don't even know if I did a good job explaining it in the live session, which is why I'm promising that I will, I will try to do a proper sort of a recap of what's all the moving parts in that question. We'll go over it, and we'll push it to the portal, or we will send a link to a YouTube video and an announcement. Whatever is possible, we'll do that really soon. Yeah.
Sir, if you could paste the previous live session link in the G space, then that would be pretty helpful.
Previous means
G
So
space,
last,
Google
yeah.
space.
So I think last run's live sessions, are they not available from the whatever NMS when you log in?
Let me check, ma'am.
yeah, it's available. All live sessions are available.
Okay.
They should be, but you may have to hunt for the one which has this. So I don't know if it's worth the trouble. So we'll see. Either I'll see if I can quickly dig it up and send it to you as a sort of something that you can look at quickly. But like I said, if you just wait for a day or two, I'll do a I think I'll do a proper review and explanation as well. Okay.
Okay. Thank you.
All right, so sounds good. But yeah, I think very thorough preparation, and good luck, with the exam to you and to all of you, and to anybody who's watching the recording later as well. I think I'll be happy to follow up with you folks one on one. I think I'm trying to revamp the course a little bit for the next offering. So any feedback you all have would be really useful as well. So. But I don't want to bother you with that while you're preparing for exams. Maybe after that, if you have some time, it would be great to have a chat. Yeah.
Yeah. Thank you, ma'am.
All right. Cool.
Thank you.
Yeah. Thanks, everyone. Thanks for joining. Good luck with all the exams that you have coming up. And see you soon. Take care.